So I'm Tali. I'm heading the Marine Imaging Lab in the Department of Marine Technologies at the School of Marine Sciences at the University of Haifa. And I'll be talking about underwater image restoration. Now, it's a short, I have only 45 minutes and a lot to say. So I try to summarize everything, and I feel it's very, it will be basic and summarized. So again, you have my contact details for further questions. Okay, so what I thought about talking about three topics. The first, to talk a little bit about what happens to the scenes underwater. So we all know the visibility is bad, but just talk a little bit about the optical effects and how they behave underwater. Then how to do basic image processing, and then a short overview of AI and computer vision methods, just to say there are many dozens of methods. So I'll mention mostly ours because they're related to the project, but also mention others and just like try to give an overview. Okay, so the time is short. Let's start with the physical image formation models. So what happens when a camera is looking underwater on an object? So if we look at the camera, and let's say this is an object, and this is a line of sight of 1 pixel from the object to the camera. So one object point is imaged into 1 pixel. So if we look at the signal that is coming to the camera from the object itself, L object is what we call object radiance, or what we like to say is how would the object look like without water? If we manage to drain the water between the camera to the object, how would the image look like? So that's L object. And so this is attenuated along the line of sight, and the attenuation is exponential. This is the equation for that. It's the exponent of minus beta z. Beta is the attenuation coefficient, and z is the distance of the object. Well, and beta depends on the wavelength of the light. This is okay. What else is happening is that there is scattering. So if you look at the same line of sight, there is light falling on each particle along the line of sight. There is light falling on it and scattering into the same pixel. Okay, so this means there is light coming to the camera that didn't start with in the object at all. It didn't touch the object. It's not affected by the color of the object. It's just coming from the water column between the object and the camera. So if we look at the contribution of just one particle along the line of sight, we have the radiance we have how much light is coming onto it, and then how much is scattered into this specific direction. So the light is scattered in all directions, but how much is scattered into a specific angle, this is characterized by what's called the scattering function. So how much percentage of the light is scattered into this specific angle that falls into the pixel we are looking at. And this is also attenuated, because if the light was scattered here, it still needs to pass all this way to the camera. So this is also exponentially attenuated. Now, I know it's very fast to go over all these equations. I want to give you the general idea of what's going on, okay? So what happens is what we wrote here is what comes from a single particle along the line of sight. But when the camera is looking into the object, we have all this line and particles along all this line. So the scattering that gets to the camera is accumulated. We have the scattering from this particle and this particle and this particle. So it's integrated all over the line of sight. So we have an integral over this expression, which looks like that. And now we want to proceed with the integral, right? Like we want to do something with it. So how can we solve the integral? We can solve it only if we assume that, not only, but a simple way to solve it is to assume that L and B are constant along the line of sight. And then I can take them outside the integral and just integrate over the exponent. So then I get this expression, and then the solving the integral, we have something that is supposed to be constant, multiplied by 1 minus the exponent, where the object here is the distance of the object. Okay, so I don't expect you to understand everything in this 1 minute explanation. Everything is recorded, but I also just wanted to give you the general idea of what's going on. So first, this is true only under these assumptions. We can assume that these sizes are uniform along the line of sight under ambient illumination, and more or less when the camera is looking horizontally. And now let's look, I see things in the chat. Are these questions to me? Because it's
no, and I will watch for you.
Sorry,
Okay.
it's difficult to read them. Okay, but if someone has a question, Perrine, what do you want to do to stop for questions?
As you prefer. Do you want?
Yeah, no, I
Okay.
prefer if there are questions to ask me. Just
Sure.
yeah.
No, so
Okay.
not for now.
Okay, so let me know if there are questions. So basically, all this we can denote it by B infinity, which means when is the term that is additive from the scattering is called backscatter, and when is it in the maximum? The maximum is when there is no object in the line of sight. So when we're looking at an empty water column and just integrating all the contributions from all the distance to infinity. So then we get the maximum backscatter, which is termed B infinity. So how does it look like qualitatively? Qualitatively, we have the signal from the object looks like that. It's decaying exponentially very fast. And the additive signal from the backscatter, it's actually increasing in an opposite way. So it goes like 1 minus the exponent. So as the object is further away from the camera, we have two effects that reduce the signal. One, the signal itself attenuates, but also the backscatter, which is covering the signal. The backscatter, I remind you, it doesn't come from the object at all. It's like it's a signal that is hiding the object. This is increasing with the distance. So these are two things happening together, with making the visibility go worse and worse with the distance. And this is important to understand. Now, from the University of Haifa in ANERIS, we are three PIs, myself, Daria Kainak, and Simon, which we worked together in the past. So this is work I did with Daria, where we showed that the equations I showed you in the previous slide, so these ones, as you see in the slide, these were developed for haze. So imaging in haze above water, and they were used also underwater. And what we showed is that it's if you use the haze model underwater, it reduces errors. It's not true. It's just it's an approximation. Like every approximation, you get errors when the approximation is not correct. And we suggested a model that is more accurate and also has approximations, but less. And the main differences between the models are that here the coefficient was the same, the attenuation coefficient. We showed that underwater it's not the same, and also that the coefficients have some dependencies, so they're not exactly uniform in the scene. And I'll just say a word why it happens. It happens because underwater, these coefficients have a strong dependency on the wavelength. And then when you look at the images themselves, in image space, we look at RGB channels. So each channel integrates a range of wavelengths. And then when the attenuation coefficient itself depends heavily on the wavelengths, there are different things happening when this integration happens. While in haze, if you think about the color of the haze, it's mostly white or gray. So there is not a lot of wavelength dependency. And that's why things are kind of, the approximation can be simpler. Okay, as again, I'm doing, everything is a fast explanation. So hopefully let me know if it's not clear. Okay, now what happens when we use lights, like Alex showed you? Then things are more complicated because the geometry is not symmetric. There are some more dependencies. So basically the same things happen when the light, now we have light from the light source. So it is attenuated on the way to the object and from the object to the camera. The attenuation is the same exponent we saw before, but there is also what's called a free space falloff, is 1 over r square. R square is the distance. This happens also above water. Every time you have a point light source, you have this falloff. But now underwater, we have both that and the exponential attenuation of the water. And we also have scattering like before, but this time it's a bit more, it's more difficult to calculate the scattering, because what happens is that light from the light source hits some particles, again, in the same line of sight, but there is a different intensity falling on these particles. And then we also have, and the amount that is scattered is also characterized by the scattering coefficient. So with artificial lights, we also have that the acquired image is a summary of the attenuated object signal and also the backscatter. But if you look at it, things are not symmetric and uniform in the picture. The backscatter has a shape. If you look at the backscatter shape here, you can see where was the light source located, right? Because you see the directionality of the light source. So you can see that the light source came from the top right corner here. And this makes things more complicated to reconstruct. So we have developed all the equations for all that. I will skip that. Just saying, you see that everything is also here dependent on the falloff of the light source. And so that makes all the integrals and everything just less simple to work with and to solve and so on. Okay, now what is the time? Okay, good. Now let's talk about basic underwater image processing. So before we go to AI and so on, I wanted to talk about a few simple things that can be done, even if you don't want to run complicated code or learning or training, whatever. There are simple things that can be done in underwater images that can already improve some of them significantly. Okay, first let's talk about contrast. So there are a few definitions of contrast, but I think all of you can intuitively think about the meaning of contrast. Or if you look at these images, we can, you'll agree with, it's just there are too many people, not too many people. I'm happy there are many people participating, but it's different. I can't wait for answers from the audience. But I think if I asked you which image here from the 6 has the least contrast, all of you will say that this one, and the most contrast is this one. And even without knowing exactly what's the definition of contrast. So if you look at the equations, the definition is you taking the maximum value in the image minus the minimum value in the image divided by their summary, and then that's contrast. So here, there will be lower and this will be maximum contrast. If you look at what happens to the contrast underwater, if you plug in all the equations we put before, we see that raw is the object color here, and we see the contrast deteriorates with the distance. So here we have this exponent minus beta d, this the distance of the object, and this is the expression for the contrast. We got that from taking this equation and plugging the model I showed you before. You'll need to trust me, and that we get this expression where you see that the contrast heavily degrades, exponentially degrades with the distance. And that's why the visibility we get is so bad. Okay, so what can we still, and we have contrast deterioration, but of course we also have color distortion, because as I said, all the coefficients depend on the color. And as you know, the water scenes look blue or green, this is because the red is attenuated usually faster. There are some water types where the red is actually not the strongest attenuation, but mostly the red attenuates much faster. And then we are left with more blue and green. So what can we do that are simple operations to improve the images? So we can do two things. One is contrast stretch, and one is global white balance. And I want to demo it on pictures. So I'll stop sharing the presentation and let me pull up the pictures I wanted to show. Okay. When I opened an image now, do you see it or it's not shared?
No, I think maybe you
It's
should
not
share
shared.
the
Wait,
full
I need,
screen.
yeah, I'll share the all the desktop. A second. Okay. Okay, can you see the picture now?
Yes,
Okay,
very
this
good.
is for this. It's my daughter, but 5 years ago, prepared this presentation some time ago. Okay, so this is not an underwater picture. I just wanted to show you what how things look like not underwater. So this is the simple Mac tool, but you know, just it's easy to demo with it. But you can, of course, do everything on other image processing tools. So when you do here auto levels, it kind of does a contrast stretch, but this image was already pretty good. It's not underwater. So you can play with the contrast here and you see what we saw earlier. But you see that things are getting kind of more, you know, black and more extreme. And you can also do white balance, which is pressing this one. And now we're doing manual white balance. So I'm pressing a white object and the image will be white balance according to it. You see there was a bit of change, everything I did, but nothing dramatic because it's, you know, it was anyway, it was a good picture to start with. Now, okay. Yeah. Okay. This is my other kid, my younger son, and here is diving in the pool. So you see that now we see the effect of the water. And let's see the same actions, what will happen. So if we now do auto levels, you see that suddenly the image is brightened. It's still greenish, but we can see a better image. If I increase the contrast, you can see a better image. I'll reset it so you see what we had before. You see? So I stopped seeing you. So, okay. And so this is what happens when we do a contrast stretch. Now let's try to do a white balance. Let's try maybe with this bubble. You see we lost, it's still bluish, but less green than what we had. And we can increase the contrast and maybe start getting not a good picture, but we can see better what's going on. Okay, so this was this image. Now this more or less worked because we had only one object in the scene, right? So it was a single distance and then we could more or less do things. Now I wanted to look at the picture. You're still seeing the pictures I'm showing, right?
Yes, perfectly.
Okay, just to make sure. Okay, here we have a more complicated scene where we have distances, increasing distances. So we have closer rocks and further rocks. So now, if I try to do the same tricks, you'll see that it's helping me less. So let's say I increase the contrast. So I managed to see these objects that are closer to me I managed to see them better and increase the contrast. But if you look at the objects behind me, it still didn't affect them at the same way. I'll do it again and look at it now. I'm increasing the contrast, and you'll see that, yeah. So when these objects are affected, the further objects are not affected yet. And this is because what I showed you before, the contrast changes with the distance of the object. So if we do a contrast stretch that is good for these ones, it will not be good for the further objects because they didn't have the same amount of contrast deterioration. Now, if I still manage to, if I do a very, very strong contrast stretch, suddenly I can see the rocks behind me really well, but this ruined the closer objects, okay? But look here on the further rocks. If I reset, look what we started from and what we can get with just, you see, it's a simple contrast stretch. So this is working locally. Every time we do some kind of a contrast stretch, it will, depending on what we do, it will affect only one of the distances in the image, not all of them. And the same as white balance. Like I can white balance according to this one, but it won't help the other color card. So this was maybe more white balance, but it still didn't solve the other areas. Okay. So for the sake of time, we'll go back to the presentation. Oh, wait, I need to turn it on again. Okay. Oh, sorry. Switch screens. Okay, so we're back to the presentation, right? Okay,
Yes.
so the conclusion from these demos was that we can do, if we have objects that are more or less at the same distance from the camera, we can do pretty basic operations, and this will improve the images already a lot. So I encourage you, at least if you take underwater images, at least do that, because it will improve the objects that are closer to the camera, and at least you'll start from a better camera. And then the objects that are further away, they will have still worse visibility. Okay. Some other simple things we can do is, if we look at using artificial illumination, usually when you look at the image, you see the non-uniformity of the light. So there are areas that are brighter and areas that are darker. So something that is pretty common to do is a homomorphic filter. Maybe some of you already use it. And this homogenizes the illumination. This is a simple thing to homogenize the illumination across the image. This helps with the stitching and stuff like that. Okay, this is not processing, but I did want to mention a few things that you can do during imaging to improve the images themselves. To avoid processing. But okay, one thing people can do is sometimes put color filters on the camera itself. So the filters will be either purple or orange, something like that. Why? Because we said that we lose a lot of red, a red color in the water, and the images are usually bluish. So if you image through something that has a lot of red, like purple or orange, this is the image you will get. So it will compensate, just make the amount of colors more uniform. Now, what's the drop? And there are many, if you look, there are some packages of filter packages you can buy for GoPros and other things. And there are also some masks that are sold, which are red. Okay. And but the strongest disadvantage in that is that we reduce light. So when you use this filter, it doesn't add red light, it just removes more blue and green light. And anyway, we're limited by light underwater. And when we use this filter, we reduce the overall amount of light. We balance the colors, but reduce the amount of light. So this is good when you have enough light, or, but the advantage is that there is less post-processing. So you get immediately you get a better picture. But again, the amount of red, like the color distortion, also depends on the distances, the same as the contrast. So if you do a fixed filter, it's good mostly also for a certain distance of the objects. It cannot correct all the objects in the same, at all the distances at the same time. And by the way, some fish also have some yellow filters on their eyes. Okay, and another thing to do is white balancing. So we could do it, I showed you how to do it in post-processing. You can also do manual white balancing underwater, and some cameras have this option that you point to a white object underwater and you do the manual white balancing. And this has an advantage, mostly if you're imaging, if you're not imaging in raw mode, if you're not taking raw images. So then what happens, sorry, if you're taking raw images, you can white balance outside water, no problem. But if you're not taking raw images, they're already, when the camera saves the images, compresses them, converts them to JPEGs, there is some loss of information. So then when you're doing, this is the same scene, but this is manual white balance underwater, and these are JPEGs. So if you're doing JPEGs, there is an advantage to do the manual white balance underwater. But again, this is per depth. So if you're changing depth during the dive, then you need to redo the white balance. Okay, and of course, if you can bring artificial illumination with you, lights, that always helps underwater. Although, as I showed you, it does introduce some non-uniformities, as you can see here. So here we can see, you see the red color in the in the nearby corals. And you see that the problem with artificial illumination is the fall off that you already know from above water. When you have a flashlight, it fades off with the distance. So this is good for nearby objects, and you can see it here. You can see that these nearby corals received light from the light source, but the ones behind did not get any light. So the closer area is colorful from the light source, but the ones behind are not. And there is also an issue of the light source itself introducing backscatter and veiling the image. So when you're using light sources underwater, you need to position them well, so not very close to the camera. Otherwise, you will have a lot of backscatter and blinding into the camera. Okay, so now to the third part. Are there questions before that?
Not yet.
Okay. I know it's fast. Hopefully it's also clear. So, okay. So there are many. So in general, maybe I should have said that in the beginning as a spoiler. This is a workshop on image reconstruction, but it's not a solved problem. So I cannot tell you how to reconstruct the images underwater. I don't have a solution yet. We are working on it, and every year we and other groups have more and more methods. So things are improving, but there is not one single good method that is the solution for everything. So there are several variants. I tried to summarize it here. First, there are methods that use only single image. So you assume you have one image and you need to do your best to reconstruct that. If you have multiple images, of course, it's more information and you can do better. There's some methods that propose having extra hardware. I will not talk about it here. Of course, there are variants about ambient and artificial illumination. There are also some variants on the goal of the methods. Some aim to make the image nice. And usually when you do that, you concentrate on the colors more of the closer objects, because usually that's most of the image, but that doesn't necessarily improve the visibility. So not necessarily it will let you see the objects that are far behind better. And there are methods that try to do more accurate color and also reconstruct the entire scene. So also the further objects. So this depends on the needs. And when we are looking on the methods, we can roughly divide them into 3 types. One is classical methods, so no before deep learning. These are usually based on image priors, and I'll explain, I'll give a few examples soon. So, and when we talk about learning methods, we have supervised methods and unsupervised method. So I'll briefly touch on all this briefly. At the end, also, there are a few review papers that can, recent ones that talk about, because really it's like not 100, but dozens of different methods. Okay. So when we look at the image formation model, this is a slide with haze, but the principles are the same, are similar. When we look at what's unknown, we have the color for each pixel. If you look at a single image input, so let's say this is the input. For each pixel, we have what's unknown is the original color. So this is denoted by J. So this is the RGB values of the pixel. And the input is we have just the RGB values of the pixel itself. But as I said, all the deterioration depends on the distances of the object. So we also have an additional unknown per pixel, which is the distance of the object. This is if we want to do accurate restoration. So then the problem is called, it's ill-posed or undetermined, because we have 4 unknowns per 3 inputs per pixel. And that's why we need to do it's not an easy thing to do, to the reconstruction. And that's why some methods introduce image priors. So the priors try to solve the underdetermined nature of the problem by adding some information. And the priors are general about images. So for example, priors can be, okay, we want the color distribution in an image to be uniform in the image, right? Because if you look at local color distribution in this one, you'll see that further away, things are more white. Or just people came up with interesting different image priors on how natural images are supposed to look like without haze or without water. What would be how can we characterize the image that we aspire to get? Okay, and I wanted to mention, oh, sorry, that's repeating. Okay. So there are many priors that were proposed. Again, I don't have time to go over them. Just recently, we did a comparison of, I'll show you underwater methods. And this one from, I think, 2018 was, I don't know, we liked it the best, the results. It's not, so this was, they also have code on GitHub. That's why I wanted to mention it. Again, I don't have time here to explain all the priors people used, but this one is a recent paper that we found that worked pretty well. And their code is also open and easy to use. Okay. Now I'll talk about a few other methods. So the opening slide of this workshop is from this paper, which called, it's written by Daria, who is also a PI on this project, and me in 2019. It's called See-Through. And what we did here, maybe I'll show you first the result. So This is the result of the algorithm. And just to say, the input is a single image, but we also require the distance map of the scene. So one of the reasons we're able to get like nice colors is that we assume we have the distance map of the scene. So this is no longer unknown. And we have it from structure for motion. So we take a few images of the same scene, reconstruct the depth, and then we're able to better reconstruct the colors. One thing is that we don't use the strength also comes from using the revised image formation model. So the one I showed you before, it gives better results, especially in further areas. And just to say, one thing, we are not using the color cards. So this image has a color card, and some people think we use it. We put it there for validation. So you don't have to have color cards to use that method. And just it's not a learning method. What we do roughly is we estimate the parameters. We use the new model we suggested, and using the depth map and the image, we basically estimate the parameters of the model and invert them. Okay, I won't go over all the stages. Okay, what we did next last year, also with Simon, who is on the project with us, is looked at what we can do if we have multiple images and we want to combine all the information to reconstruct the scene. So we used a framework called NERF, Neural Radiance Fields. This is a very famous paper, and that has thousands of consequent works in computer vision. And what we did is we developed the NERF to work underwater with the underwater image formation model equations, and we showed that it can clear the scene. So I'll show you a few movies. Just the basic NERF takes a few images and learns basically an MLP, a neural network that can represent the scene. And then it learns how the scene looks like from every viewpoint. So this movie is a rendered movie. It's not a video that was taken. They took a few input images, then the network learns to represent the scene from different viewpoints. And then to render the movie, you can ask it, okay, how would the scene look like from this viewpoint and this viewpoint, generate several viewpoints, and then generate the movie. Now, when you take it underwater, so we did the same with, okay, let's do it underwater. And you see that the result of the basic NERF is not good. You get all these clouds because it doesn't know how to model the water. So for the network, then the water is like a blue object, and it tries to model it, and you see that we get clouds and the representation is not good. So what we did, we inserted the underwater image formation models, and for the sake of time, these are the input images. And we are able to reconstruct the scene without these clouds, or maybe with a little bit, but so this is our result. But what's more important, because this is compared to the original one, and the left is ours, but this is still with water. But because this framework enables us to represent the entire scene, we can also render the scene without water. And this is what you see on the right. So this is taking the NERF and telling it, okay, now render the scene, remove the water component. So this enables us to render its novel viewpoints, so how the scene looks like from different viewpoints, but also without water. And take a look at the further parts that are reconstructed. Okay, we have more. This is another result where on the left, both of them are our results, but this is in water without the water. Look at the corals that are further away, how we can expose them and expose their colors. And this is another scene. Everything is on the project's website. I know I'm almost out of time. So you can appreciate it there. And the code is also there. And also, last thing I wanted is to mention a recent work that is in review. I just want to say I skipped talking about supervised methods. So I didn't prepare a slide about it, but I'll just say a few words before I explain that about supervised method. For supervised method, you need a training data set. And this is pretty difficult to obtain underwater because you cannot just remove the water from the scenes to get the ground truth. So it's very difficult to get a training set of the underwater image and the ground truth. There are a few data sets that try to overcome that. The one that is most used, it's called UIEB. And what they did there, they took underwater images and they tried to restore them using different methods. So tried to restore them and then took the best one as the ground truth. And then most of the supervised methods use that data set to train on. This is, it's getting good results, especially in like scenes that are closer, maybe a bit less complicated, but you train, I mean, note that the ground truth is generated by restoration methods. And as I said, we still didn't find the perfect restoration method. So the ground truth is generated by restoration methods that are not perfect. So the result is limited, the quality is limited to that when you use that as a training set. That's why we tried to do, and this is part of also the ANERIS project, to do an unsupervised method using diffusion priors, which is also a hot topic in computer vision these days. So the paper is in review, and also don't have time to explain what we do, but basically diffusion models, it's what's used in DALI and everything to generate images. So the diffusion prior holds a lot of information on how images are supposed to look like, because if you've been using DALI to generate images and all that, it has kind of all the information about all the images in the world or many possible images. What we did here is to use it to try to reconstruct the image. So to take the input image and tell it, okay, listen, but you know how images in the world are supposed to look like. They're supposed to be colorful with contrast. It's not like that. So try to give us an image that will explain the input image. But it's not so simple because there are many different explanations. So we use the underwater image formation model to constrain the reconstruction, and also we output a depth map. So this is the result of this method, is to use this input image, and the output is both a reconstructed image and the depth map from the input image. The problem with it is diffusion models run on low resolution, so everything here is pretty low resolution. Hopefully that improves in the future. Just for this work, we did a comparison. There is a list of methods here, like many recent methods. So I don't know if you can appreciate, it's a bit packed, the slide. This is our method, this is the input. By the way, this is the simple contrast stretch, which you see, it's not so, I mean, it gives you decent results without an effort, and sometimes better than other methods, because the other methods sometimes fail, right? I mean, and I think, yeah, so I mentioned, we saw here, sees the GDCP I mentioned. Here, actually, its result is less good, but here it's pretty good. And yeah, and what's that? That's a paper called MMLE, which is also kind of decent. Yeah, and if hopefully you see that in our result, the further area is much better reconstructed. Okay, so this was a bit of self-promotion. I mentioned there are a few, this is a good review paper, and also another review paper of all the different variants of restoration methods. Again, no one has the perfect method for the same scene. Some method will work better, and other scenes, other methods will work better. Each method has its assumption, the training set, and all that. So that's something to look at when you're looking at restoring images. And that's all. Okay. So hopefully I'm on time. And if there's still time for questions.
Thanks a lot, Tali. That was blow-minding. Yeah, I'm so impressed by the different constructions that you make. I cannot see right now any question, but I have a question maybe during the time people are raising the hand. So basically, I have two questions which are related to each other. So in your image formation model, so basically there is this relationship between the image quality and the distance. So first question is that could you just use the image quality to construct the distance map? And then the related question is when you do you need the distance map for most of the approaches that you're developing, and from structure, from motion, I believe it's more like relative distance, not absolute distance that you would get, and how sensible it is, and this kind of considerations.
Yeah, okay, these are two excellent questions. So it means maybe some of what I said was understood. So as what you asked about image quality is a really good idea, and some image prior used it. There was what's called a blurriness prior. They tried to estimate basically the distance using the reduction in contrast. It works. It actually works pretty well, but it's, again, nothing is perfect. So because the image contrast also depends on the objects themselves. So it's not like exactly one-to-one measure, but yeah. And also I mentioned you need the distance, but not all the methods reconstruct the distance. So some just, as I said, some try to improve the image quality, and they do not use the distance explicitly or try to reconstruct it, but try to do a kind of a local image quality restoration. I wanted to show the equations to understand what's behind it, why it's not an easy task, and why it's getting more complicated when there are many distances in the scene. If you just have one fish versus the camera, that's okay, that's easier. So yeah, but some methods just try to look at the quality and color and optimize for that regardless of the distances. So yeah. And the other question is also very good, but the thing is we have relative distance maps, everything that I showed, but it's okay because we also don't have the coefficients themselves, we estimate them. So this is coupled with the absolute distance map. Yeah, so that's why I don't know if in one of the slides I had transmission, because some people reconstruct the multiplication of the attenuation coefficient and the distance, because they're coupled. So you don't have one of them in absolute units, but you also don't have the second one, and that's like it goes together.